The integrated circuit, or microprocessor, has shaped the modern world. A chip of semiconducting material, usually silicon, covered in electronic circuits seems relatively mundane, but without them, 21st century living would be unrecognizable. Polymers are indispensable in the manufacturing of integrated circuits. Photolithography is the technique by which all the circuits within the microprocessor are produced. A silicon chip is coated in a photoresist, a layer of material that allows for specific patterns to be etched into a substrate and exposed to intense light. The photoresist can either be positive, meaning that the areas exposed to light are etched, or negative, where the unexposed areas are etched. A common positive photoresist is Novolac, a polymer similar to bakelite. The polymer is mixed with diazonaphthaquinone, DNQ, derivatives, which stops the Novolac dissolving in an aqueous base. When exposed to light, the DNQ undergoes photolysis to produce a carboxylic acid that no longer inhibits the dissolution of the polymer in the aqueous base, so the exposed region of photoresist may be removed. Negative photoresists often consist of a polymer that is soluble to developing fluid in the form it is applied, but when the polymer is exposed to light, many cross-linkages form between polymer molecules, hardening and insolubilizing the final product, as that it is not removed by the developing fluid. A different method involves photopolymerization via a free radical mechanism, which is more common in larger circuit printing. An initiator molecule is added that absorbs ultraviolet light to produce a free radical that attacks monomers to form a highly cross-linked polymer. Photoresists are an excellent display of how the properties and reactions of polymers can be put to use to benefit an industry. Looking to the future of microelectronics, many items of wearable technology are becoming available. An issue arises from the necessity for small conducting wires to carry electrical signals. These wires are often quite fragile and susceptible to breakage, leaving the device permanently inoperable. One solution to this is self-repairing wires formed of a polymer core that can repair after breakage, and a coating of carbon nanotubes or other small-scale conductors. When the polymer breaks, it can repair itself and re-establish the electrical connection, allowing for wearable technology to become thinner and more durable. Following on from the wearable technology, let's look at self-healing polymers for other applications. Polymers can fail due to internal damage to the polymer matrix. These microcracks are almost undetectable from the outside and are impossible to repair with conventional means. The theory is that polymers with the ability to self-regenerate or repair will not be susceptible to these microcracks, as they will be filled as they form by new material. One method of producing polymers that are capable of repairing themselves are living polymers. These are molecules where the reaction is not terminated when the supply of monomer is exhausted, so the addition of further monomer allows the chain to grow in length. This method is especially useful in space technology, as the harsh radiation that materials in space are exposed to will often create radicals. As living polymers can be produced that contain radicals, this allows for the capture of any monomers that become radicals from exposure to ionizing radiation. Many self-regenerating polymers are designed in a vascular style, inspired by the vascular networks of plants. These designs are called biomimetic, as they attempt to mimic the natural world. A vascular polymer has many small, fragile glass vessels, millimeters in diameter, embedded within the plastic that are filled with a resin-based structural filler that seals the microcracks as they propagate and then cures to provide a comprehensive seal. Another method that allows for polymer self-repair is using microcapsules containing monomer or resin in a liquid form. The material itself is then filled with a dispersed particle of catalyst for the polymerization of the monomers or curing of the resin. As a microcrack spreads into the plastic, the capsules will rupture and fill the crack via capillary action. As the crack spreads further, a catalyst is encountered, and the rapid polymerization inside the crack seals and prevents further damage. One commonly used sealant is dicyclopentadiene with a Grubbs catalyst. However, this has drawbacks that prevent it being effective for mass production, so an alternative, 5-ethylene-2-norbornene, was discovered. ENB undergoes polymerization much faster than dicyclopentadiene, but it forms an inferior straight-chain polymer rather than a highly cross-linked one, making the healing material more likely to break in future compared to dicyclopentadiene. Many different methods of microcapsule self-repair have been studied, with free monomer and encapsulated catalyst, or by attaching the catalyst to the exterior of the microcapsule. Some research has also been done in photocatalyzed reactions for this application, as not needing a catalyst can improve the lifespan of these materials and is potentially cheaper and more robust, as there is one less point of failure within the repair process. The effect of containing microcapsules in the plastic has also been studied. reporting an increase in the toughness of epoxy with microcapsules up to 127% that of pure epoxy. Despite this, the vascular approach is often more desirable due to its ease of integration into a plastic. The microcapsule method can also use living polymers like those described earlier, wherein the rupture of the capsule allows the living polymer to enter the crack and react with polymer chains that are exposed, filling and sealing the crack. Some polymers are self-healing without any additional monomer or catalyst, but instead rely on reversible polymerization to refill and reform the internal structure of the plastic. These are sometimes not considered self-healing as they require heat to repair. Thermal energy breaks the covalent bonds in the polymer, forming smaller monomer particles that spread into the microcrack before the removal of heat allows the cross-linked polymer to reform into its original shape, effectively removing the crack. An example of this category of regenerative reactions is between multifuran, molecule 1, and multimalamide, molecule 2. The reaction produces polymer 3, a highly cross-linked polymer with thermal reversibility. The future of self-repairing polymers is in this process, wherein more polymers are discovered that show the capability to reorganize under specific conditions to repair a plastic. More modern approaches are leading to polymers that can do this at room temperature, allowing for these polymers to make their way into ordinary products.